Hello students, this video is supplemental to the vectors and vector analysis lab, or lab number 2 for this semester. There are some concepts that I normally would talk about in the lab if we were actually meeting face to face. I felt that it was most appropriate to make a video to give you the best way of trying to discuss these ideas. So basically the vector analysis lab is primarily associated with vector addition. That is the main concept that is being studied in this lab. Now we can go back to the chapter 1 lecture. We can review a lot of that because I covered a lot about the vector addition in that lab. However, I'm going to review it tonight and kind of go over a couple of the different problems in the lab. And so we have a good idea. And I'm also going to talk about the adding vectors graphically. We haven't really covered that. I covered it somewhat in the last lecture, the chapter 1 lecture, but I really haven't covered it in enough detail, I don't believe. So I'm going to give a lot more emphasis on that tonight. So there's 3 ways. In the first original lab, when we met face to face, there were 3 parts to it. And this lab, interestingly enough, is not really does not really employ experimental equipment very much. It actually is kind of a part lab, part science, part art kind of lab. And so in so doing, the original lab had 3 parts to it. Essentially adding vectors 3 different ways. The usual way that we do in class would be what we call the analytical or algebraic method. And again, that's if you look at the last video, that is a method by adding component by components. All right, so this is the usual way that people add vectors. All right, the other method, second method that would also be in the original lab, and I did talk about somewhat, but not deeply enough in the chapter 1 lecture, is the graphical method. And I'm going to speak a lot more carefully, much more carefully on that tonight. Okay, and then the third method that was employed in the original lab that we met face to face would have been called basically adding vectors using what's called a force table. Now, the force table employs Newton's second law in an equilibrium setting. Essentially, you have strings attached to a central ring, and you essentially will add weights, attach weights to the end of the strings over a pulley, and essentially the weight causes tension in the strings, and you essentially will study the tension in the strings as forces, and you would then add up the forces. We're not going to do that tonight because we can't employ that equipment. We can't meet face to face. So instead, again, in the current form of the lab, the online form, you still do the first 2 methods, but we now will replace the force table with the PHET simulation software, which we talked about a couple nights ago. Okay, and so that's the part of the lab. That's the first part of this lab, is the simulation software. Essentially, simulating vectors, basically picking up vectors off of a little side table, putting them onto a main grid, and then adding vectors that way, and basically making your own vectors however you wish, making them as long as you like, at whatever angle you like, creating a couple vectors, and then selecting the check box that says sum, and you get what's called a sum vector, and then you get to see what the magnitude and direction of the sum vector is, right? And that's what that software is about. So that's what we have now in the online software. Well, we talked about the PHET software together. What I want to focus on tonight are these other 2 methods a little bit more. Now, again, I'm going to spend a little bit more time talking about the graphical method. since I did spend a good amount of the chapter 1 lecture talking about the typical method, analytical method. But I'm not gonna neglect you. I am going to go and review the analytical method some more, and so do not worry. All right, so I'm going to erase this. And particularly, I want to focus on a couple of different problems in this book. And so what I want to do is want to take a look at a couple of different problems. The first problem so again, if you go back to the lab, you'll see that you go to it says finding a resultant vector, algebraic method. Those 5 steps, steps 1 through 5, are going to directly involve the PHET software. And again, we went over that together. Then you go to a section called exercises. Now, exercise number 1 and number 2 are also being performed by the PHET software. I'm not going to cover those. Essentially, you will do the addition of vectors and the setting up of a vector utilizing that software, and to be able to directly answer questions as given. What I want to focus on tonight are what would be covered in exercise 3. And I don't want to do everything for you. I want to do case 1 and case 3. While I discuss case 1 and case 3, I will try to drop information along the way that'll help you answer the post-lab questions, the questions toward the end of this lab. All right, and so if you're listening carefully, I will mention answers to those questions as we go along. All right, so in the meantime, let's talk about case 1. All right, so case 1 wants us to essentially add 2 vectors. So we have 2 vectors. So again, I'm looking at exercise 3. Okay, and I'm particularly looking at case 1. I'm going to work out case 1 and case 3, and I'll leave you to do case 2. All right, and so case 1 says I'm going to get a couple of vectors that are expressed. So I have a vector A. Okay, I put the hat on to denote it as a vector. I have 2.94 newtons. At 20 degrees. And that's exactly as it's written. And then vector B says 1.96 newtons at 110 degrees. Okay, I want to add those 2 vectors. Now, if I'm not told anything else with respect to any kind of axis, then I am to assume that I'm going to do a counterclockwise rotation from the positive x-axis. So let's draw out what these vectors look like. So again, I'm going to do my Cartesian coordinate system. Basically a fancy way of saying xy coordinate system. All right, and this is x. This is positive x, positive y. I'm going to establish my orientation. Positive x, positive y, negative y. Okay, so 0 degrees would be going straight from the origin along the positive x-axis. And then you will do a counterclockwise rotation. So here's like 30 degrees, 45 degrees, 90 degrees. Here's like 120 degrees, 180 degrees. I'm sorry, I got 180, 270, all the way back to 360. So again, if you're not told anything else, it is a rotation. There's 360 degrees around a circle. Half a circle is 180. So where do I draw these vectors? Well, I'll draw 2.94 out, and again, it's bigger than 1.96. So I'll try to make allotments for those differences, and I'll say that's about 20 degrees, because I know that there are 90 degrees in the first, the first quadrant. Okay, so that's what that's going to be. So I'll say this is, and I'll say this is the magnitude of A. So I'll put a, I'll take the hat off. It's going to be that size 2.94. Write it out. Newtons. Again, these are forces. Forces are vectors. Really, we're going to look at vectors in a mathematical sense, so it kind of more or less doesn't matter what they are yet, because we haven't even studied forces. That's a chapter 4 concept. But again, a vector is a vector, and so force is an example of a vector. Okay, where would I put the other one? 110 degrees. Well, this is 90, and about 20 degrees past that would be 110. So it won't quite make it as long. And we'll say this is vector B, 1.96 newtons. And I have a couple of choices. I can either specify this as a 20-degree angle with the y-axis, or I can specify, I know that these are complementary angles, so I can specify a 70-degree angle with the negative x-axis. And typically what I like to do that. I like to try to keep some sort of consistency. I mean, it's perfectly okay to do this 20-degree angle if you wish. But again, as I said, there's always 8 different forms of angles. And so it all depends on what, I mean, I can have a 20-degree angle this way, 20-degree angle this way, a 20-degree angle with the x-axis. What I like to try to do is I like to try to make some consistency. I have an angle here with respect to the positive x-axis, while I have an angle on the other side with respect to the negative x-axis. And that way, my equations look a little bit consistent. And it's really a person's choice. All right, so that's what I have here. So again, I'm going to go over the algebraic method first. And why do I do that? Because I'm going to talk about the graphical method in a moment, but I'd like to get an idea of what my answer actually looks like before I actually start drawing the graph, and we'll talk about that in a moment. So I have everything I need to know here. So when I'm expecting here now again, all I really care about are local triangles when I try to go and add these vectors up. So what I'm going to do is I'm going to break apart this problem, and I'm going to basically solve the components of vector A first. And again, for me to be able to do vector addition, I have to specify each vector in terms of its components. You have to do that before you actually are able to add the vectors in the first place. All right, so with that said, let's remind ourselves here that I want to just extract a triangle at this point. I'll worry. So this triangle's, and I mean, basically I can think about this as being a right triangle because I know the axes are orthogonal, as I mentioned in the chapter 1 video. But I really don't want to worry about or plus and minus signs of the dimensions quite yet. What I just want to do at this point is extract out this triangle and just work on a triangle. And then I'll worry about what quadrant it's in later. All right, and so it's going to essentially extract out this triangle. And I know that the hypotenuse is A, and it's going to be 2.94. And I'm not going to worry about newtons right now. We'll worry about that later as well. All right, and then this is a 20-degree angle. And then see, I want to break it up into its x component and its y component. I want to express this vector as so much of the vector in the x direction plus so much in the y direction. Again, we're going to put it into components. Again, I'm going to kind of review from the chapter 1 lecture. So this particular length along the x-axis, we'll call it a sub x. Okay? And the particular length along the y-axis, we'll call that a sub y. All right. And then we have to employ trigonometry. Okay, so again, as a review from the last lecture, I know that with the hypotenuse, I know an angle, and I'm looking at the adjacent to this angle. When I use adjacent and hypotenuse in the same sentence, I should be thinking about a cosine, right? And so cosine theta. Again, reminding yourselves of what we talked about last time. Adjacent. Now review your trigonometry if you don't remember this. Over hypotenuse. All right. And so what does that mean in our language? This particular problem, well, cosine theta is going to be the adjacent is a sub x. I don't know what that is yet. I'm solving for a sub x. Divided by, I'll just say capital A. Capital A is the length of the hypotenuse. I'll cross multiply, and I find out that a sub x is a cosine theta. Okay, and so now I'm in a position to solve for it. A sub x, a sub x, remember, is a, well, what is a? 2.94 times the cosine of 20 degrees. All right, and that comes out to be, so I go to my calculator and I put in a cosine of 20. Okay, remember, make sure your calculator's in degrees. So cosine 20 comes out to be about 0.9396, blah, 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 times 2.94. Comes out to be 2.76. Let's see if I can write this better. At the end of the, okay, so a sub x, when I do this, is 2.76. Can I get that by multiplying? So let me kind of just rewrite this down here. I think I'm off the camera. So a sub x, okay, is 2.94 times cosine of 20 degrees. All right. And you do that, you get this, 2.76. Okay, again, I don't care if it's positive or negative at this point. All I care about is this local triangle. All right, and so I'll just kind of leave it written as is. I'll give you a few seconds. And then I want to work out the a sub y. Again, I have a limited whiteboard, so I'm going to be doing a lot of erasing. All right, I'm going to erase it now. We're going to work out a sub y. And just like last time, let's see here. I want to understand a sub y first. So again, I erased my triangle, so I'll try to reassess this picture here. Again, this was a sub x, and this is a sub y. Okay, a sub y, remember, is I know the hypotenuse, and now if I take this angle and I kind of just extract out, the opposite leg is the a sub y. So when I use words like opposite and hypotenuse together, I think of sine, right? And so the sine of theta is I'll just write it out, opposite over, sorry for my handwriting here, over hypotenuse. All right. So again, in the language of this problem, the opposite is a sub y. And the hypotenuse is just the magnitude of the vector we call a. Cross multiply, I can write that a sub y is a sine of theta. Remember, this little y here is nothing but a decoration. It is a subscript. It says that this is the variable in and of itself. This is just a sub y. It's the part of a that's in a y component. Okay, so it's not a separate variable. It's really a decoration. All right, so working it out, a sub y is the 2.94 That's the length of the whole vector, the hypotenuse. Sine of 20. All right, so a sub y. See if I'm still on the video here. All right, so I think the sine of 20 should be a small angle or a small number. It's about 0.342 times 2.94. I get 1.01. Okay, all right, so with that said, I have worked out the components. I'll just write it up here for the moment. All right, now we'll worry about sines, SIGN, later. Okay, I still have to work out B. All right, so again, I'm just going to worry about a triangle and just lengths of a triangle. I don't care about sine shit. All right, so B, it looks like a triangle. It's another right triangle. I'm going to go with the 70-degree angle because I kind of like, I mean, if I can, my convention is just to basically work on triangles that are kind of similar to or alike, and that, you know, I have triangle. This triangle has a vertex angle around, you know, with respect to the x-axis. Well, I'm going to try to do the same kind of thing. So my equations look somewhat similar. When you get more advanced, you can, I mean, maybe you could work this triangle out instead, and that's perfectly fine. So let's just kind of do things. We're just kind of getting started here. So again, I'm trying to work out B. So the first thing I got to do is work out B sub x. So I imagine having well, essentially pulling out a triangle. Looks like this now. And it's not very representative. It looks more like a 70-degree angle, I guess. All right. Again, we'll just pretend that's 70 degrees. And I have B, the hypotenuse. The length of that vector is 1.96, as we were told. I'm not going to worry about newtons right now. And just in the same token, I have a component in the x direction and a component in the y direction, b sub x and b sub y. And I got to do the same mathematics as before. I'm going to be a little bit more of a shortcut now. It's the exact same mathematics I did before. The cross multiplication, everything else. So I'm going to just write it out now. And again, as I progress, I'm going to start just writing these things. So b sub x is what? It's b cosine theta, exactly as I did before. And this being the adjacent, this being the hypotenuse, I just did 2 steps of algebra in one. That's all I did. All right, so b sub x is my b, 1.96, times the cosine of 70 degrees this time. All right, b sub x, if I do that, I get 1.96 times the cosine of 70, and I get about 0.67. Okay, now, I could probably start talking about the signs, right? Because the A is a first quadrant triangle. Okay, so again, when the first quadrant, you know, a first quadrant vector, I apologize, is going to have a positive x and a positive y. So these are both positives. But b sub x, this is a second quadrant vector. It's going to live in the second quadrant, you have to have a negative x and a positive y. This is really going to be negative, and I might as well just indicate so now. So I'm going to erase this a little bit here, so I get a little bit more real estate. So I'm going to say that b sub x is negative 0.67. All right. Employ the signs. Leave the local triangle. Remember what I'm doing. It's a physics problem. You know, remember the overall problem that I'm doing, and realize, oh yeah, I'm looking at a vector that's in the second quadrant. Okay, now I have one more calculation to do. I have the y component of b. So what's that going to be? That's going to be the I have an opposite and a hypotenuse. So remember again, I'm just going to kind of remind you of the steps of algebra, review them, done them a few times now. And now I can write that b sub y is b sine of 70 degrees. What is b? Again, what did I do? I realized that I had the opposite of my hypotenuse. I know that's equal to the sine of theta. I cross multiplied and got this. Okay, so again, the exact same steps of algebra. All right, so b sub y is 1.96 times the sine of 70. And I find out that b sub y is, I got the sine of 70. Okay, put that in your calculator. You get about 0.9396, blah, blah, blah. Multiply by 1.96. You get a number like 1.84. And this b vector is actually a second quadrant vector, so that 1.84 is actually a positive 1.84. So I have all of the components that I need, and I'm ready to add the two. I'm going to erase all this stuff right here. We know what we have. We already know what vectors we're adding. So let's now go through the process of adding them. Now that we have the components, how do you add two vectors? Now, here's one of your vocabulary terms from the lab. The sum of two or more vectors. I mean, we did talk about this in the chapter 1 class, but anyway, the lab asked this question as well. The sum of two or more vectors is called the resultant. Okay, again, that's something that is a question in this lab. So again, I'm pointing it out to you. The resultant, it is a term. You add up vectors, you get what's called the resultant. We want to calculate the result, so I'll actually call it R in honor of the name resultant. So R is A plus B. Again, looks very similar to the kind of arithmetic that you're used to, but it's as I said in the chapter 1 lecture, it is a totally different kind of addition. It is the addition of vectors. So the addition of vectors is done by component by component. So we add vectors, component by component. Okay, that means that I'm going to express R. I've done all the work to get the components. I know that R is going to be A. Well, what is A? Well, A is going to be this much in the x hat plus this much in the y hat. Remember the x hat, y hat, the unit vectors? So I'm going to say I have positive 2.76 x hat plus 1.01 y hat. Again, a sub x, x hat plus a sub y, y hat. Plus, I got B. B is negative 0.67 x hat. Again, my B. Again, negative now, x hat. And then plus 1.84 y hat. Okay, I've expressed A explicitly. I've expressed B explicitly. Now what do? Well, we combine like terms, just like in algebra. We imagine these x hats and y hats to be like vectors, and you combine like terms. So you'll say that R is going to be, I get my x hats together. I have positive 2.76 minus 0.67. 2.76 minus 0.67 x hat plus. Okay. Y hats. I have 1.01 from A and 1.84 from B. 1.01 plus 1.84, all multiplied by y hat. I'm just combining stuff now. Now I got to go and do arithmetic. Let's see if I have enough space here. the resultant vector r. So again, I just put in my calculator. It's nothing but a simple subtraction. 2.76 minus 0.67. You get 2.09. X hat. 1.01 plus 1.84, 2.85. Oops. 2.85 y hat. That's a brand new vector. Now, interestingly enough, we have to ask ourselves the question, where does this new vector live? Well, I have one vector that is first quadrant, added to another vector, the second quadrant, and it turns out that the resultant vector, let's see, what vector, where does it live? Well, it has a positive x and a positive y, and that puts it in the first quadrant. And so, as I've said in the past many times, how you get a vector is how you need to return the vector, right? And so I now know what my vector is, and so I can pretty much not worry about the components any longer. Now I'm dealing with r. And so remember, I was given two vectors, was angle and direction, and so now I need to return. I was given two vectors with magnitude and direction. I need to return the resultant in the form of magnitude and direction. Okay, so again, that's what we have to do. And so we have this vector. I'm going to write it up here to conserve space. So I have this vector r. It is 2.09 x hat plus 2.85 y hat. There it is. So we got to do now is figure out its magnitude and direction. So again, I already answered the question, where does it live? Again, I'm just going to redraw my axes, plus x, plus y, and negative y. Well, if a vector has a positive x component and a positive y component, it is a first quadrant vector. So r, whatever it is, lives in the first quadrant. This is my r, and this is its theta, and I don't know what that is. What I do know is the following. I do know r sub x. I also know r sub y. I can read it right off the vector. R sub x, literally just reading the vector. R sub x is the x component, 2.09. All right? And r sub y, to literally read it off the vector. R sub y is 2.85. Again, I'm being very deliberate to mention positive signs and negative signs. Why I keep on red 4 there. Okay, so what I would then do is to find the magnitude, use Pythagorean Theorem, and so I would know that r, the magnitude of the vector r. Then I'm gonna employ Pythagorean Theorem, but then take the square root of both sides. I'm going to do 2 steps of algebra in 1. So r is really going to be the square root of r sub x squared plus r sub y. Let me be a little bit more deliberate. Remember Pythagorean Theorem. So again, I kind of went over this probably fast, but remember back in your geometry days, if you have a right triangle, length A, length B, hypotenuse C. Remember the Pythagorean Theorem? Again, gotta make sure we get enough math review in. Pythagorean Theorem from the Greek philosopher Pythagoras, the mathematician Pythagoras. Pythagorean Theorem. Remember that it was c squared is a squared plus b squared. That's all I'm doing. All right, and so that's the Pythagorean theorem. I'm going to employ that here. I know that this vertical is going to meet the x-axis at 90 degrees because the xy coordinate system or Cartesian coordinate system is called an orthogonal coordinate system. That means the axes are perpendicular to each other. All right, so I do know this is a right angle. This is a right triangle. All right, let me erase them. Pythagorean Theorem, and let's just employ it. Now what I'm going to do, again, I know that c squared is, well, just write it down, r squared is r sub x squared plus r sub y squared. So instead of having a squared plus b squared c squared, I have r sub x squared plus r sub y squared equals r squared. And then I can basically take the square root of both sides. R is the square root of r sub x squared plus r sub y squared. Take the square root of that. I take the square root of both sides. And I can plug the numbers in. R, okay, is the square root of 2.09 squared plus 2.85 squared, square root. Okay, so what do I do here? How do I figure this out? Well, again, I take 2.09 squared. That gives me basically 4.3681. I add it to 2.85 squared. When I add these two squares, I get like 12.4906. Okay, just so you're keeping along with me. I'll take that value and take the square root of it, or the 0.5 power of it, and I will get 3.53. Okay, so the length of this vector is 3.53. Okay, okay, so now we know that what the length of the vector is. The other thing we need to know is, we know its magnitude, we now need to know its angle. So I'm going to write this 3.53 down. I'm going to I'll just erase some of this. Actually, I'll write it here on the side. So R is 3.53. And again, I'm not going to put a sign there because remember, a magnitude is signless. It's like an absolute value. I'm going to erase this now. Now what we got to do is work out the angle. Now that I know the magnitude or hypotenuse, I can actually use sine, cosine, or tangent. Typical one does though is they kind of assume that you don't know the hypotenuse yet, and what you have coming to the problem is just the components, and so you'll use the tangent. And a reminder, so for the tangent is, again, that tangent of theta is the opposite divided by the adjacent. And going back to our trigonometry review, for those, some of you haven't had it for a while. Tangent of theta, well, let's see, it's not always y over x, but again, in this case it is. So I have r sub y, that's the opposite. The adjacent is r sub x. So I have r sub y over r sub x, or theta. I'm going to take the inverse tangent, or the arctangent of both sides. The arctangent of a tangent just gives you the angle back again. And then, of course, the arctangent on the other side is just the arctangent. We also call it tangent -1, or inverse tangent of r sub y over r sub x. Okay? And doing another step of algebra here, I'm going to plug the numbers in. So theta, let's put it up here actually. Theta is now going to be the arctangent, or the inverse tangent of putting the numbers in. Okay, r sub y. Again, I just want to put, pause the lengths in. Again, I have a local triangle. 2.85 is r sub y. Divided by 2.09. Now, hypothetically, I mean, I'm really talking in newtons, but it doesn't really matter, because the argument of a trigonometric function, or really the argument of what we call transcendental functions, which can be sine, cosine, tangent, logarithm, exponential, any of these kind of functions, the argument must always be unitless. It must always be a pure number. So even though I'm not worrying about units, I mean, this would be newtons over newtons, and newtons would cancel. If you have units inside of an argument of a trigonometric function, or a transcendental function in general, then there's a problem. You never want units in a trigonometric function or a transcendental function. All right, so I'm going to take the inverse tangent now of 2.85 divided by 2.09. And when I do that, I find out that I get 53.7 degrees. All right, so what I have done is I've taken the two initial vectors A and B. I found their components. I added, so R equals A plus B. I added the two vectors component by component. I obtained a vector R, the resultant vector, in component form, but I really want to return the vector in a manner in which I got it, particularly because I'm trying to compare it with the graphical method. And so what I now have is this 2.09 x hat plus 2.85 y hat. I now calculate using Pythagorean theorem. I find the magnitude and I find the angle. And to really write this out properly, I could write it in a couple different ways. I mean, I would write it as this way. I would say R is 3.53 newtons. I mean, I am doing a physics problem. This is a problem with forces. So 3.53 newtons at 53.7 degrees above positive x-axis. Now, generally speaking, I can just leave, I mean, in this special case, I can leave off the positive x-axis because if you don't say anything else, then you know that you're talking 53.7 degrees from the positive x-axis anyway in a counterclockwise rotation. All right, so that's what I'm expecting. I mean, that is my answer. Okay, that's from doing the algebraic method. So what I'm going to do is I'm going to save this off and kind of write it up here. So I'm going to compare this number with what I get from the graphical method. Okay, we're going to talk about a different method in a moment. So this is from the algebraic method. I'm just going to kind of remind ourselves what that is by putting it up in the corner here. So 3.53 newtons at 53.7 degrees above the positive x hat axis. So I'm going to erase all this other stuff. I'm just going to write the final answer in the upper corner and move on. Okay, this is just for our reminder. This is the answer to the algebraic or the analytical question number. I guess it's the one for case 1. This is the answer for the algebraic case 1. Okay. So again, I want you to show your work. Just don't write this down, and I want you to show your work and work this out yourself. Okay. I don't want you just to throw me this answer and that's it because you saw this video. I want you to do all the work that I just did. Work your, walk through the work, show me all the steps, and turn that into me. Okay. Now, what is the graphical method? We just got done doing the analytical method. We're now going to talk about the graphical method. Now, to do this, what do you need? You need graph paper. Okay, the usual green gridded graph paper works just fine. You need that. You need a ruler or some, fairly, accurate measuring device. And you need a protractor. Okay? We're not going to do really any math in the analytical method. In the graphical method. In the analytical method, that's your mathematical method. The graphical method, you're going to get the answer by measuring. Okay? So, you have to be very accurate. And so before you do anything, what you want to do is, I'm just going to kind of write some basic stuff down here. You want to fill up the, 8.5 by 11 graph paper with your graph. Basically your vector package, your vector diagram. Okay, I don't want a tiny diagram taken up, in some corner of your graph. That doesn't tell me anything. You want to actually, the larger you make your graph, the more accurate it is. All right, and so why do we want to do that? Well, essentially, with a little graph, you're going to get answers. You're going to essentially be able to give the same answer you got with all this trigonometry. You're going to be able to do that through measurement only. So if you have a tiny diagram, it's not going to do any good with the measurements. You want a larger diagram. So a larger diagram is easier to read and more accurate in obtaining measurements. That's why you don't want some little dinky diagram. You want a larger diagram that takes up a good part of the page. So how do you do that? Well, the first thing you have to do is essentially figure out the scale. All right, and so anytime you have a map, let's say for instance you have a map of Texas, and you go on Google Maps or something, and you want to take a trip, let's say from Fort Worth down to Houston, and so you'll get a map, and essentially the whole map is going to fit on an 8.5 by 11 piece of paper, or on the display of your cell phone, and so or on your computer screen. And what you'll see oftentimes, you'll see something like this. You'll see some, you might see your map. Let's say here's Fort Worth, and here is Houston, and you're gonna go, basically down, to Houston, various, stops along the way. Not a very pretty map, but you'll see that, such and such a length, whatever is equal to, 50 miles or something. And so you can kind of go along and figure out how far it is from Fort Worth to Houston on your map, and you'll basically have a scale. Because you're taking basically you live toward the top of Texas, you're going toward the bottom of Texas, and you have to try to fit all that on a fairly small piece of paper or small display on your computer screen. So you have to have a scale. You have the same problem here. And so we're faced with, let's kind of go back and talk about what our problem is again. Remember, we have again, it's the same problems we had before. 2.94 newtons at 20 degrees. And we have B, and that's 1.96 newtons at 110 degrees. And that's the problem we're faced with. And so we have to look and say, well, I need to try to draw a graph and fit it on my paper. And one of the things I'd like to do when I do the algebraic method first is kind of figure out which way is my graph going. When I add vectors up, is my resultant vector going to be more maybe first quadrant, or is my resultant vector going to be more second quadrant? So if I know it's going to be more second quadrant, I don't want to go and start my graph way off to the left side of my paper, because I'm not going to have enough time. If it's a second quadrant answer, I'm just not going to have enough space for me to be able to draw the vector out. So I probably want to start the vector maybe toward the middle of the page, or if it's going to be second quadrant, maybe the middle in the lower part, to basically give myself enough room to be able to draw the vector. So doing the vector algebraically first gives me an idea. I know that the vector is going to be 3.53 in size. I know it's going to be first quadrant. So the vector is going to be kind of heading off this direction. So my whole picture is going to be kind of going northeast, if you will. And so what I would do is I would go to my graph paper very, very carefully, and I'd say, well, first of all, I need to figure out what a good scale might be. And you're going to have to be very accurate. The more accurate you are, the better your answer is going to be. So you might say, well, I don't know. Let's see, if I want to do, how about 2 inches per 1 newton? So let's just say, for instance, I'm just going to pick a scale that I think has worked from experience, and I would say that 2 inches is equal to 1 newton. So essentially, if on my paper, I would have, basically 2 inches, that'd be 1 Newton, and I'd have a total of about, let's see, I guess, yeah, probably about 6 inches ish will be how big this will be across. And so I would say, okay, I have 2 inches, it's going to be 1 Newton. And so what I'm going to do now is I got to figure out, again, we're talking about, yes, the diagram represents forces, but we don't really care at this point. We're just going to represent forces in a distance space, if you will. We're going to essentially represent it just as vectors. There's lines with distances, and understand that the lengths of those lines, these lines represent forces. Okay, and so my scale would say 2 inches is 1 Newton. All right, we'll say, okay, I have 2.94 newtons. How long is that going to correspond to? So I would do a simple, the only math I'm going to have to do in this method is just the simple proportion math. If I know that basically 2 inches per 1 Newton, the question is, how much, and this is an Algebra 1 problem, what is my force, what is my length for 2.94 newtons? I'm just doing a simple proportionality problem. That's all I'm doing. And so I'm going to cross multiply, and I would realize that x is going to be, 1 times x is x. It's going to be equal to 2 times 2.94 newtons. Again, you might find out that 2 inches is not a good approximation. But I think in this case, it looks like I think it is. So 2.94 times 2, about 5.88. Now, again, it's really hard to measure 5.88 inches. You can do your best, but you're going to have some error. It's kind of a fairly crude thing, but you're going to have to kind of estimate what about 5.9 inches actually is. All right, and so I would say that my A, if I'm doing the scale, my length of my A, which is, let's see, I'm just going to write this out. My length of my A, and I need to write this down, is 5.88. Let's see, it corresponds to 2.94 newtons, and that corresponds to a length of 5.88 inches. Again, it's not pretty. Some people might have better scale factors, but again, there is some error associated with this. But again, I'm representing vectors in length space, if you will. Okay, I'm representing them as lengths. All right, I would do the same kind of thing for B. So again, same scale factor, 2 inches per 1 Newton, x over what? In this case, x over 1.96. Again, very simple scaling. No sines, no cosines, nothing advanced. All right, and so what I would then do, and again, x, all it's representing now is just a length. So cross multiplication, 1 times x is x, 2 times 1.96. And I find out that x is going to be 1.96 times 2, 3.92, almost 4 inches. So again, remember what my B is. It's 1.96 newtons. And that also in my inches space, I'm not going to say that's equal, I'll say that transforms, if you will, into my length space of 3.92 inches. Otherwise, it looks kind of crazy to say that a force is equal to a length. It's a transformation from force space to length space, if you will. All right. That's all the math I really have to do. Everything else is careful measurements. So how do I do this? Well, I'm going to understand, if I'm doing the algebraic method, what my diagram looks like. And I nearly know that I'm going to be talking about first quadrant vectors, so I'll probably go closer to the left bottom of my graph. And remember, the graph paper is gridded. So I'm going to find a grid point, nice grid point, and I'm going to call that my initial origin. And then I'm going to use my protractor. I'm going to put my protractor such that it's, such that there's a little hole in the bottom of the protractor, right? In the center, you put your protractor along this hole. The protractor looks like this. And you figure out where's 20 degrees. So say 20 degrees is here. You'll basically take a pencil, you make a little dot here, and maybe another little dot where the 20 degrees is. You pull away your protractor, and you very carefully, don't just draw a line, freehand. Basically put the straight edge on basically connecting both of these dots and draw a very nice line. That's exactly or close to it of 5.88 inches. So you'll figure out exactly what 20 degrees is, or your measurement of it. So here's 0, here's 20. 20 will be a marker. For those who haven't used a protractor, will be a marker on the protractor. So again, what are you going to do? You're going to put a little dot right in the hole. That's what that hole's for. Put a dot there. You'll put another dot right at 20 very carefully. You'll pull away the protractor. You'll pick your straight edge, a ruler, and you'll connect the two. Okay? And so when I do that, I'll have something that's about, again, this is not gonna be, I'm drawing this not to scale because I'm just, the confines of my whiteboard and the fact that I don't have these devices that I'm asking you to have. So here's this grid point on your graph, and let's see, 5.88 inches. Again, this is not going to be 6 inches by any means, but I'm going to try to do my best to make this look like it's a 20 degree, 20 degree angles and about that length. Okay, that's your A. So remember, what are you doing? You're doing R is A plus B. So you draw down, you draw your A first. Again, you're reading from left to right. Your A first. You're going to draw it on the paper. Let me actually draw it a little bit lower. Give myself some space. That's a grid point that I pick. I have very carefully drawn a line at 20 degrees. Imagining this being 20 degrees, this being the line that would be very close as you can to 5.88 inches. Remember, 5.88 inches, and our choice of a scale corresponds to 2.94 newtons. Okay, that's your A. Now, we're going to do tip to tail. So, as I said last time, we're going to take, so again, I'm going to draw, this is my A. I can put a little A here, if you will. I'm going to draw a separate origin now. I'll put a little arrow here to indicate it's a vector. I'm going to add B. I'm going to put a brand new origin. Whether there's a grid point there or not, I'm going to imagine there being a brand new origin right here at the tip of A. I'm going to go tip to tail. I'm going to put the tail of B at the tip of A. So I'm going to get out my protractor. I'm going to line it up with this new coordinate system. And I'm going to say, well, let's see, what am I now? Let's see, I'm 110 degrees. That means in my protractor, I'm going to read at 90 to 110. So it's going to be it's going to be like 20 degrees past the vertical. On my protractor, 110 to be somewhere out, say here. It's not going to be as long as A. It's going to be about instead of close to 6 inches, it's going to be close to 4 inches. And so going from there, again, I'm going to try to do the best I can here. All right, that is, we'll say, that's my B. Okay, you're going to do this not freehand like I am. You're going to do this with very careful measurements. You're going to take your ruler. You're going to make sure that's as close to. You're going to make sure that you have a point, another point determined by the protractor and the little center hole in the protractor. You're going to connect those lines very, very carefully. You're going to try to make it as close to 5.88 inches as you possibly can. And then you'll make a brand new coordinate system, just brand new little coordinate origin for B. And you'll get your protractor out. Again, make it, you have a point there and figure out 110 degrees. Figure out where that is in a protractor, connect the lines, and make sure that line is as close to 3.92 inches as you can. Okay, that's A plus B. Again, you put, again, you read this left to right. You draw A first and you draw B. Tip to tail. B is drawn at the tail of B is at the tip of A. Tip to tail. Tail of B starts at the tip of A. Okay, what's the last thing you do? Well, the resultant is always drawn from make this look nicer. The resultant is always drawn from the tail of the first vector to the tip of the last vector. It turns out that I can add any number of vectors this way. Again, that may be a question on your lab. How many vectors can be added with the graphical method? 2 or more. Now, when I do case 3, I'll show you a case where we'll have 3 vectors we'll add this way, right? Right now, we're just doing 2. How many vectors can you add through the algebraic method? 2 or more. I can add 20 vectors this way. It'd be painful, but I could do it. Okay. Tail of the first to the tip of the last. So I get my ruler out again, and I very carefully draw a vector from the tail of the first to the tip of the last. See if I can how successful I can be here. It's actually not too bad. That is my vector R. So I'm going to figure out. I'm going to measure this length. And then I do the corresponding, scale factor. I'll then know what the corresponding force is. Okay, and I can know the angle by literally getting my protractor out and figuring out what is the angle from along the origin of the first origin, the origin in which A sprouted from, to R. That, if things are done well, we figure that out. That should be about 53.7 degrees. We hope. It won't be. It'll probably be 54, 55. I mean, there's going to be some error. And then you should realize that, what you should get, so you're going to get, when you're going to measure, so when you get done doing this, you're going to measure some value for R. So you will measure length of R with your ruler. And you'll get it, some length. And remember that length corresponds to, so there's going to be a length of R. Okay? And that's going to correspond to so many newtons. And so remember, 2 inches corresponding to 1 newton. We just got done measuring R. It's a length, and that's going to correspond to, let's do it a little bit differently. I'm going to do my proportion a little bit differently. 1 newton per 2 inches. Now, I don't know what this particular force is. I'll just say, I'll say that's my length. That's my actual force R divided by, let's just say that I measured this and I get L. So this is my R, but let's just say when I go to my ruler and I measure this, I get some length L for my ruler. So I go to my ruler, I take my ruler out, and I measure the length of this vector that I'm calling R. But what I really want to do is figure out what that force is. So how do I do it? Well, I basically cross multiply, and I realize that I cross multiply here, I get 2R equals L and that r is going to be whatever that length is that I measure divided by 2. And you hope that that length is going to be about, say, pretty close to 3.53 newtons. So that L is going to be on the order of, say, 7 inches. So it's going to be fairly large. You might find out that maybe 2 inches is a little bit big, but I think it'll fit on your graph. I mean, if you're doing something like that. But anyway, you're going to measure L. L is going to be right around 7 inches. Should be okay. I mean, it's going to be a big, graph that's going to take up most of your graph paper. And then you take that 7-ish inches divided by 2, and you'll get some value that you hope is close to 3.53 newtons. It's not going to be 3.53. Maybe it's 3.5. Maybe it's 3.58. There's going to be some error because this method is as crude as the measuring device that you're using. You're measuring a ruler and a protractor. So there's some error associated with that. And so your experiment is going to have error, E-R-R-O-R, because of your measurement. Okay, that's the graphical method. Again, how do you do it? You figure out where A is. You figure out, first of all, a scale. And from your scale, you now know what lengths correspond to your force magnitudes, your vector magnitudes. You very carefully draw that length at a particular angle, measuring that angle with the protractor. You draw it out anywhere on the graph paper you wish. And then you do the same thing, but now you have a new origin, B, and then you figure out its length, and you draw a corresponding angle with respect to that axis. Then your resultant is a line drawn from the tail of the first to the tip of the last. You convert that length back to force or back to whatever the units are. It could be velocity vectors or whatever. In this case, it's force. And then you'll measure that final vector, that angle with the protractor from the original, from basically the origin you used for A. You'll measure it with the protractor and you'll get your answer. And again, this is called the graphical method. There is the only math associated in this method is just a real simple math to do the scale factors and the proportions. There is no trigonometry associated with the graphical method. There's very little math, mostly measurements. The algebraic method, that's where you do all the trigonometry. That's your purely mathematical method. All right. So this is case 1. I'm going to just do one more thing in this video, and that's case 3. All right. Again, I've kind of answered some questions already, so I'm going to erase the board here. So this gets case 1 out of the way. Now, please do this yourself. You're going to need to turn in the graph. So again, as part of your work that you turn in, you're going to need to turn in, I would say get some, printer paper, work out the mathematical details of the algebraic, adding by components, and then work out the actual graphs on graph paper. Very accurate graphs, not something sloppy. It's got to be on graph paper. It's got to be with a scaling factor. You tell me what the scale factor is, and it's got to be done with care. Okay? All right, so that's case 1. I'm now going to do case 3. All right, so case 3. I'm going to go back to the lab real quick. All right, case 3 says we have 3 vectors now. All right, a little bit more painful. We have a vector A. Okay, A is going to be 1.96 newtons at 10 degrees. Let's see here. B is 1.47 newtons at 90 degrees. And C is 2.45 newtons at 160 degrees. All right, so make sure I got that right. 1.96 at 10, 1.47 at 90, 2.45 at 160. All right, that's what I have. Okay, so those are the three vectors I want to add. One second here. All right, so let's locate these vectors on a graph. All right, so again, we're going to do that just like last time. Let's get them. Let's try to make the mathematics as tangible as possible. So do a Cartesian coordinate system: plus x minus x plus y minus y. Figure out where these are. So I have 1.96 newtons at, say, 10 degrees. Okay, so that's 10 degrees, is not much. So again, I'm doing a mathematical method first. So we'll say 1.96 at 10 degrees. It's just math. That's 10 degrees. This is A. Magnitude of A is 1.96 newtons. All right, there it is. The second vector, it's not quite as long, 1.47 newtons. That's at 90 degrees. So 90 degrees is straight up along the y-axis. So 90 degrees, the whole vector is entirely in the y direction. This is my B. So that vector there is B. Its magnitude is 1.47 newtons. Okay, so that's right along the y-axis. And then C. Well, C is 160 degrees. Okay, well, remember, halfway around this unit circle is 180 degrees. So I could draw this a couple different ways. I'm choosing to draw this as a 20-degree angle right here. Again, 160 plus 20 is 180, supplementary angles. I like to draw angles such that I call it hugging the x-axis, if you will. I'm essentially drawing the angles to be, I'm forming them with respect to the x-axis. All right. And again, this is C, and the magnitude of C is 2.45 newtons. All right. So really, it's just going to be deja vu. I mean, I've already done this. I'm just going to do it with three vectors now. Just a little bit more work. Luckily, this one's going to be pretty easy, so it won't be too much more work. Okay, so let's work it out like I did before. I'm going to try to be a little faster than before. So I have A, and again, I'm going to go through the same mathematics as before. A sub x, A sub y, look at a local triangle. So I don't care about signs quite yet. And I would have realized that A sub x, again, I'm going to try to go a little faster as we progress in the class. A sub x is A cosine 10 degrees. All right, so A sub x, what is A? That's 1.96. I'm not going to worry about newtons right now until the end. 1.96 cosine 10. Again, it's cosine because I'm looking at the adjacent leg along the x-axis. And again, that's A sub x. A sub x, I get up my calculator, and I say, okay, cosine of 10, that's a angle, it should be pretty close to 1. Cosine of 0 is 1. So cosine of 10, 0.9848. Again, that's pretty large because 1 is as big as you get. Times 1.96, you get 1.93. Okay, that's what. Again, I'm just caring about a length of a triangle right now. A sub y, similar math. Again, remember the y component would be the opposite. A sub y would then be 1 point. Put one more line in here. A sine of 10 degrees. Okay. A sub y would then be 1.96 sine of 10. I find, again, I'll do this with you, sine of 10, I get a number like 0.1736 times 1.96, I get 0.340. All right, those are my components. And again, it's mostly x component and not too much y component. But let's remember these. So I'm going to kind of put these, write these up. So again, I have limited whiteboard space, and so try to conserve real estate the best I can. So I'm going to write it up here. A sub x is 1.93. And a sub y is 0.34. Okay, so that's what I have. And at this point, I can assign SIGN signs to them. Well, it's the first quadrant vector, so it has a positive x and a positive y, so these are both positive numbers. So I can be explicit about that if I wish and say that these are positive. All right. Okay, so I'm done with A. Now, B is actually quite nice, but I'll try to be methodical about B. And I realize that the angle for B is 0. And it really is going to be, the angle for B is going to be at 90 degrees. Well, let's remember here, if I were talking about a cosine of 90, the cosine of 90 is 0. So one of those you have to remember in your MCAT. So if I'm going around talking about, if I were to say explicitly that, again, if you take a look at this, you really don't have to do this, but I'm going to try to be explicit. If I were to say that B sub x is B cosine of 90, and B sub y is B sine of 90. Well, if you put cosine of 90 in your calculator, you realize you get 0. There is no B sub x component. I mean, this will be 0. You can just look at the graph and see that. And sine of 90, again, you need to know this for those taking the MCAT. Sine of 90 is 1. So sine of 90 being 1, you just get B. All of the vectors in the y direction. So that's nice. So B sub x is 0. B sub y is just B. The whole thing. 1.47. And that is along positive y. So it is a positive sign here. Okay. So that's not too bad. And then one more vectors. I have C. Again, I'll draw out the triangle particular for it. I'll extract it. I have this triangle. Again, I don't care about the signs of the dimension as because I'm just extracting a local triangle. And all I have is a local triangle with lengths, 20 degrees. And again, I have C sub y, C sub x. And I'm just going to work out, I guess I'm a little bit off the C sub x. There you go. I'm going to work out the, and this is C. Work out the trig here for this third one. So again, as is usual, the C sub x is an adjacent with hypotenuse. So we can write it as C sub x. Again, I'm just caring about lengths right now. C sub x is going to be C sine of the angle, not the 160 degree angle you talk about. I mean, that confuses things and adds extra negative signs and stuff like that. Why don't we just get a local triangle with a 20 degree angle? And so it'll be the sine of 20. All right, so you're not involved in 160 because we know that 160 plus 20 is 180. All right, and so C sub x will be the C, 2.45, times the sine of 20 degrees and c sub x. Work out the math. Sine of 20, 0.342 times 2.45, 0.838. All right, and that's what I get there. Actually, I got this backwards as a cosine. I apologize. Cosine 20. Just looked at that. Looked funny. Cosine is the adjacent. All right. That didn't seem right. Yes. So again, I apologize. I was doing things quickly here. Cosine is the adjacent hypotenuse. So again, that's supposed to be a cosine. I apologize for my mistake there. Cosine of 20 times 2.45. So scratch what you just saw. You should see instead 2.30. Again, adjacent hypotenuse is cosine. All right, 2.30, and I realize that this is a second quadrant vector, so second quadrant means a negative x and a positive y. So I'm going to apply a sign of negative x. Now let's write it up here in my little parking lot. So c sub x is negative 2.30. I'm just collecting my results. All right, one more calculation to do for components. Now this time we use the sign. All right, here we go. Now, c sub y is the opposite. Opposite hypotenuse is the sine. So again, using the same math as before, c sub y is c sine of 20. C sub y is 2.45. Sine of 20 degrees. And I find out that c sub y is, all right, sine of 20, 0.342 times 2.45, and that's going to be 0.84. We'll say. All right, and given that this vector, the c vector, is a second quadrant vector, that's a positive value. That's a positive component. So there we go. So we have all the information we need, positive 0.84, and we're ready to now do the arithmetic. All right, and so all I have to do at this point is add them component by component. I'm going to erase this diagram to give myself some more space. And now I'm going to essentially do what? Again, two or more vectors added together gives you a resultant. So R is A plus B plus C. I'm adding three vectors now. Doesn't matter, I can add 20 vectors, I get a resultant. It's just adding up a bunch of vectors, you get a resultant. All right, so R is going to be A, expressed as x component, y component. So positive 1.93 x hat plus 0.34 y hat plus, what's B? Well, B is nice. I mean, I'm going to be very methodical here. It is 0 x hat. Nothing in the x hat, but I'll just, I don't even have to really write this term. I'm going to write it anyway. And then plus 1.47, the whole vector, y hat. Plus, finally, C. Okay, this, one way you can mess yourself up is for forgetting your signs. Negative 2.30 x hat plus 0.84 y hat. All right, so I'm going to add all these up. I get that R. Okay, so I'm going to do what? Well, all my x's. 1.93 plus 0. Contribution from B minus 2.30. It's a little bit difficult. x hat. Okay, and then plus, again, I apologize for the nasty nomenclature here, 0.34, just putting all like terms, so combining all the x's now, combining all the y's, plus 1.47, plus, just adding numbers, 0.84. Y hat, multiplied by y hat. Okay, I'm going to erase this stuff now. Kind of write this all together now. So, I get my calculator out and I say, okay, I got 1.93 plus 0 minus 2.3. I get negative 0.37. X hat. All right. Here I'm just adding a bunch of positive numbers. So let's say I have 0.34 in the y's plus 1.47 plus 0.84, 2.65. Y hat. All right. And so, so that is our R. It's A plus B plus C. So I don't really need to worry about A, B, and C any longer. I now have a brand new vector. Remember, you add vectors up, you get another vector. I now have a new vector R, so I had A, B, and C, and I'm not going to worry about those until I go to the graphical method. So I'm going to erase everything except this result. And again, what I want to do, I have this R, and I got to go and convert it back into the way I was given the vector, and that was in magnitude and direction. So again, let's put this up and get it out of the way. R is negative 0.37 x hat plus 2.65 y hat. Right, that's what I have. What I need to do now is write it back to the direction. So again, I'm going to use Pythagorean Theorem. And well, first of all, let's figure out where this vector actually is. So I have to figure out what quadrant it's in. So I had a couple of I had three vectors. I had one that I had A that was entirely in the first quadrant. B was straight up along the y-axis. C was in the second quadrant. Turns out that my final vector has a little bit of a negative x and a lot of positive y. And so something that has a negative x and a positive y, that's going to be a second quadrant vector. So it's very stubby in the x, so it's going to be mostly y. It's going to have a large angle with respect to the y-axis. So I'm going to kind of write it like this. That's my r. This angle here is theta. That's going to be fairly big. All right. So again, I know this because the x is fairly stubby in its size. The y is much bigger than the x. So I have an idea what my vector looks like. All right. So what is r? Well, I'm going to use two steps in Pythagorean Theorem. It's going to be r is the square root. Now remember, it's negative 0.37. That negative is squared. Don't do like some students do and go negative and then put 0.37 squared. No, the negative 0.37 is what is squared. Okay. Plus 2.65 squared, and that's going to be under a square root radical. R is, okay, so remember, negative 0.37 squared is going to be a positive number. So negative 0.37 squared, I get 0.1369, plus 2.65 squared, I get 7.1594, for those doing the math with me. And then, of course, I need to take the square root of that number, or the 0.5 power of it. I'll get 2.68. I mean, my calculator really says 2.6757, wherever, but I'm going to round up to 2.68. All right, so you won't see 2.68 directly in your calculator. I rounded it. All right, now what I want to do is figure out the components, oh, sorry, not the components, but the angle. So I do know, again, looking at a local triangle, I do know that this r sub y length, and I know this r sub x length. Looking at a local triangle, I don't really care about the signs at this point. I just have a local triangle. And so I know that the theta is going to be the inverse tangent of, in this case, opposite over adjacent, which in this case is particularly r sub y over r sub x, which is the inverse tangent of, again, lengths. Don't care about negative sign. The y is 2.65. The x is 0.37. And just doing lengths. Don't worry about negative or positive signs. Theta. Okay, so inverse tangent of the local triangle. 2.65 divided by 0.37. I get 82.0 degrees. Actually, rounded, I guess I can call it 82.1 degrees. 82.05 is what the calculator says. All right, so there you go. And so you have this. So your final answer is going to be, I'm going to erase this stuff now. Again, I'm just trying to conserve space. So what I would actually write is that my final resultant R is 2.68 newtons at 82.1 degrees from negative x-axis, or if you want to specify it a little different way, you could say, well, I know that this whole angle is 180 from the positive x-axis, so I could say 180 minus 180 minus 82.1, or 97.9 degrees. So I could say, or R is 2.68 newtons at 97.9 degrees, if you wish. Understood that this is 97.9 degrees from the positive x-axis. Both ways, it's fine. So all in all, I expect a vector that's going to basically be in the second quadrant and at a pretty large angle, 82 degrees ish from the negative x hat axis. Okay, so I have that expectation when I go draw my graph. Now I got to go do the graphical method. All right, so let's remind ourselves what this looks like. So again, I'm going to erase the board here. So this is the first part, the algebraic part of case 3. Okay, so now we go to the graphical method. And at least I have an idea of what it looks like. I know it's going to be overall a picture where my graphs are going to have more of a, I would say, a northwest type tilt to them, if you will. So I'm probably not going to want to draw them, in the far left part of my paper. I'm going to probably want to maybe start in the middle and allow some space. And I might make a different choice about my scaling factor. So again, you can play around with that, but I'm going to do the graphical method. I'm going to use the scaling factor that I used last time. You might find out it doesn't work, so you can try a different scaling factor, and you can preserve a scale. The same math applies. Okay, so again, what is the problem? Let me go back to the actual lab again one more time. Make sure I get it right. Okay, so again, case 3 is 1.96 newtons at 10 degrees. Okay, this is the last part of the video, is the graphical part of case 3. 1.47 newtons at 90 degrees. And finally, C is 2.45 newtons at 160 degrees. All right, and so for lack of a better thing, I'll use my scale. So I'll do my scale here. I'll say, well, we'll say again that 2 inches in my scale is per 1 Newton, right? Again, I'm not doing this. Is the part of the problem where you don't do you do the very basic elementary math, right? You're not doing any more trigonometry. That's done. 2 inches per 1 Newton. All right. So again, we did this already. We said that was some length divided by 1.96 newtons. So effectively, it was multiplied by 2. And again, we said 1.96 times 2 was 3.92 inches. So again, my A, I'm going to kind of put a little on the side here. I'm just going to put a corresponding length in shorthand of 3.92 inches. We understand that as the corresponding length and length space for this particular force. I would do the same thing for B. Instead of 1.96 newtons, I want to figure out how big 2.45 newtons is. Then I cross multiply. And I find out that at least in this particular case, I end up multiplying by 2 again. So 2 times 2.45 is 4.9. This corresponds again to 4.9 inches. Again, how did I do this again? Remember, cross multiplication. X times 1 is X. This way it's 2.45 times 2. I sometimes tend to go a little fast, and so I want to make sure that I'm not going too fast for anybody. All right, that's all I'm doing. Lastly, I'm sorry, 4.9 is this guy. I did the bottom part first. This is 4.9. All right, I have the middle part to do, and that's simply 1.47. So I stick 1.47 in here, and 1.47 times 2. 2.94, all right? Those are my corresponding lengths. Okay, now what I gotta do is get out my protractor, my ruler, and another piece of graph paper, and very carefully draw this out. So I'm probably gonna not go as far to the left and the bottom, starting like I did in the last one. Probably going to want to be, I can start toward the bottom, but I want to kind of move over a little bit more to the right, maybe more toward the center. And I'll start with my little grid point, some grid intersection. I say, okay, now let's see here. 3.9 for newtons, around 4, I'm sorry, but that's around 4 inches, sorry, 3.92 inches is very, just barely less than 4 inches, and 10 degrees. So I get my protractor again, and I will have to very carefully measure an angle. My protractor 10 degrees is very slim. So again, I put my protractor, again, protractor looks kind of like this, right? Figure out where 10 degrees is. I'll put a dot in the center of the protractor, center bottom. There's always a little hole there. 10 degrees, figure where 10 degrees is. Put a little dot on your paper, right, lined up at 10 degrees. Take your protractor away and draw your line. So again, take away your protractor and draw a line that connects those 2 points. So I would have that point out here, and I got to draw the lines and very carefully draw it such that it is as close to 3.92 inches as you can get. So again, drawing something like that. And my drawing is not to scale, of course, and my drawing is also freehand. You're not going to want a freehand drawing. All right. Now, tip to tail. This is A. Now, B, well, B, again, you're going to go, the tail of B starts at the tip of A. You're going to draw a, imagine your coordinates is right at the tip of B. and you realize in your protractor, again, you want to do this carefully. You want to put your protractor and you want to literally line up a point that's at 90 degrees. You don't want to just eyeball it. You literally want to put a point that's at 90 degrees. You draw your little point there, and you take away your protractor. And again, let's see, this is not quite as long as 1.96, so I should see something look straight up. That is my B. Great. But I have one more. I have to add C. So what I got to do now is I got to put a coordinate origin at the tip of B. Again, you want to do this very accurately. You don't want to be doing it like I'm doing it. You want to make sure you're doing it very, very accurately. So at the tip of A, and you're going to start a new one. You say, okay, well, it's going to be 2.45 inches or 4.9 inches. And it's going to be at 160 degrees. So 160, as we recalled, was about 20 degrees from the horizontal axis, negative horizontal axis. And so it's going to look something like, I'm just going to put this in here to kind of help myself here. It's going to look something like this. It's going to be longer than the first one. So it's going to be like something like that. All right. And so, again, you're going to want to do it in such a way that it is, that it's accurate. And this is my C. A plus B plus C, tip to tail. You draw B at the tail of B at the tip of A, then you draw the tail of C at the tip of B. You have three vectors drawn very accurately. Now, how do you do the resultant again? It is a line drawn from the tail of the first to the vector to the tip of the last vector. The first vector is A. You draw the line from the tail of A to the tip of the last vector to the tip of C. So my line is going to end up being drawn very carefully with your ruler. It's going to be drawn, again, let's see how good I do. Art is not my strong point. Actually, I'm doing pretty well tonight. That's your R. Okay? So again, you very carefully measure these. And what's left to do? Just like last time, right? You got this R. You're going to, first of all, you'll measure what R is with respect to the protractor. Put a protractor here. And you hope that you get a value that's around 97.9 degrees. Or 82 this way, 82.1 this way. So again, you're hoping when you do this measurement, this angle's right around 97.9 degrees, or what did we measured last time? Okay, that's your angle. So you'll measure again. You'll measure angle of R with a protractor at the origin of A. Okay? So again, origin of A, measure the angle of R. I mean, everything you're doing here is through measurement. And you get theta. We'll call this is your theta of your resultant. And then you want to measure R. What do? Well, you're going to measure the length of R. And let's just say that we call this length, just like last time, we measure this very carefully. We'll call this L. So we say, well, okay, let's see, what do we know again? We know that, let's see here, 1 Newton mate. 1 Newton corresponded to 2 inches. So I got this R, which is basically a magnitude of whatever this force is, corresponding to L inches, whatever L is that I measure. And remember, we did the cross multiplication. L times 1 is L. R times 2, in this case, was 2R. I mean, if you have a different scaling factor, yours would be R times whatever that scaling factor is. You might find out that 2 inches doesn't work for you. But anyway, so I find out that R, in this case, would be L divided by 2. Now, or L divided by whatever your scaling factor is. All right? And so you would retrieve from this length, you'd retrieve your resultant force. And again, any number of vectors can be added this way. We added 3 vectors this way. Any number of vectors, 2 or more vectors can be added through the algebraic method. 2 or more vectors can be added through the graphical method. All right, so I'm going to erase this. And let me see if there's anything else that I might be able to answer in the lab questions before we call this video a done deal. Let me go back to the lab real quick and see if there's anything else that I might like. So I'm going to have you do case 2 by yourselves. And that one's for the student. I mean, really all 3 of them should be for the student, but I'm trying to be a nice guy. Let's see here. I answered a lot of these questions. Under what special case can vectors be added via the Pythagorean method? Well, that would be if the vectors are at right angles to each other, right? Pythagorean method is done because for triangles that are right triangles. Number 6, how do you graphically determine the components of a vector? How do you graphically determine the components of a vector? Well, again, if I find out that after I add A and B graphically, let's say, for instance, I get some sort of a vector R. And so let's just imagine here for a moment that I add A plus B, so R is A plus B. I'm trying to answer number 6 in the lab. All right. If I do that, again, be careful here. It's saying number 6 is saying you're adding graphically. Okay, that means you're doing the tip to tail business, right? And let's just say I do this. I'm just giving an example here. So I draw out my vector A and I draw out my vector B. And I'm just making up something here. And I find out that I have a vector R. Okay, so R is really just another vector. How would I determine its components graphically? Well, I would understand that this is just another vector. So I could take my ruler, take my protractor, and very carefully draw a perpendicular to the x-axis. And then I would determine what R sub x was by measuring it, right? So I'm going to take very carefully whatever my vector R is. I'll draw a perpendicular with the help of my protractor to the x-axis, and I would measure this length. That would be my R sub x in my length units, right? And then I would do the same thing. Again, I'm not doing any trigonometry. I'm literally just measuring. The length of that vertical would be R sub y. And what would I do? Well, I would say, let's see here. I would say that 2 inches, or let's see, 1 Newton per 2 inches. Make sure I'm on the board here. 1 Newton per 2 inches will be what? R sub x per whatever length I measured. So I'll call this L sub x. That's how I measure a length L sub y, right? So I measure that length and I say, well, that's that length of, I measured L sub x, and I can just basically say, well, I do the cross multiplication. I realize that basically R sub x is L sub x divided by 2. If I use this, again, I would say L is 2R sub x divided both sides by 2. And I would say the same thing going through the same math. And again, this 2 supposes that you use this particular scale factor, right? And I would do the same deal with R sub y. I would measure it, that length of the vector, and then divide by the scale factor. So again, if you were to go and have a new vector, through graphical means, you can get to its components by literally, very carefully drawing a triangle and figuring out what the horizontal length is and what the vertical length is, and basically convert those to forces. All right, that would be the answer to number 6. All right. Anything else I can help you? 7 is briefly describe the steps involved in adding 3 or more vectors using components. Again, describe what I just got done doing in case 3. Describe that in words. Describe that exactly what's going on. What am I doing? The trigonometry, the components, adding the components, adding the vectors component by component. What did I do there? All right. Let's see. What else? I'll let you. So number 9 says, why does making the drawing of a graphical determination of vectors have less error to make the graph as large as possible? I mean, I talked about that. If you make the graph, the larger you make the graph, the easier it is to take the measurements. Right? You want to try to make precise measurements. You're really going to have a hard time if you have a little dinky graph and you're going to try to get information out of that. The bigger the graph, the easier it is to measure it is. It's kind of like looking at a magnifying glass. You have everything blown up. It's a lot easier to look at small details. Number 8, vector subtraction is addition of a vector in the opposite direction. For case A, what would be the result of R equals A minus B? You may compute the answer by either analytical or graphical methods. I mean, I would say you probably want to use the analytical method, but I will tell you how to do number 8, and I'm going to leave you to be the person who does it. All right. So number 8. Okay, if you recall, you can put these numbers in yourself. I got down and I understand that I figured out an A equals A sub x, x hat, plus an A sub y, y hat, right? And again, those we know those numbers. I'll just give those numbers to you again, just so you know what they are. They were. This was 2.76, and this was 1.01, okay? Just as a reminder. B, I mean, I really want you to do this. B sub x, x hat, plus B sub y, y hat. Now, let me help you here. So A sub x, remember, was 2.76. A sub y was 1.01. B sub x was negative 0.67. B sub y was 1.84. Again, you can look back earlier in the video and see this, or look earlier on your work and see it. Okay, I'm not going to do this problem. I'm just going to kind of tell you how to do the problem, okay? Remember, if I want A minus B, I'm going to take a difference vector, I'll call it R still. I'm going to say A minus B. It's really going to be A plus the opposite of B. And remember, the opposite of B, I get that by just basically multiplying each of the components of B by negative 1. All right, and I'm going to leave it at that. I'll let you do that. Because remember, if I have a vector A, and I want to multiply by some scalar little a is actually it's S for scalar. So again, scalar, remember, is just a number. Just a number. I want to write S times the vector A. I know the vector A is A sub x, x hat, plus A sub y, y hat. So I distribute the number to each component. So SA will be S A sub x, x hat, plus S A sub y, y hat. Now imagine, in this case, that S is negative 1. What would happen? All right. So if it's negative 1, I basically put the negative sign and distribute each one, right? And so I'm gonna let you do this. I did talk about it last time. I gave an example in the chapter 1 lecture, but I do want to leave some stuff for the student to do. Sorry. So that, again, this is problem 8. All right. With that, I'm going to close the video. This, again, was a supplemental video for the vectors lab, which is lab 2.